let's just do a high-level overview of the sorts of different microstructural models that you can construct, okay? So you could start with a whole bunch of discs, and we can overlay on that these joints, okay? And so we can create, we think of that as a base material, and we can overlay joints on there. We can carve out material to make voids. We can go, and here's a collection of white discs. And then on top of that, we had a scanning electron microscope image of concrete. And then we identified by coloring them the guys that are supposed to be the aggregate in the concrete. And then what we can do is say, okay, for all the yellow things, we give that a bonded particle set of properties corresponding to the aggregate. It's probably stiffer. And the yellow and the white guys are going to be the mortar. And then there's white yellow guys, which are going to be the interface. And so now suddenly we've built the bonded particle model that is a multi-phase material by simply identifying particle groups in different ways. And this is a compression test has been done, and you'll see a slide a little bit later of this. And these are the bond breakages. And in this case, the breakages are going in the mortar. All right. Again, these you can build compact, or you can also build porous rock, right? Here's the big overview, the basic idea again, grains joined by cement. Now I'm going to start talking about grains, and I'm going to start talking about cement, okay? The grains are rigid, they don't change their shape because these grains are actually PFC particles. But the cement is embodied in the contact model. And in general, depending on the type of cement, the type of contact model, this cement can itself be deformable. Remember the parallel bond. It's parallel because there's additional springs due to the cement. So that the cement can be deformable and the cement can break. Bond can break. And we're going to see it can break. It can partially break as well in some of these models. So there we go. The grains are particles, balls, clumps, rigid blocks. The cement can be, well, it's the type of contact model. So contact bonded, parallel bonded, flat jointed contact. And when the bond breaks in these systems, it behaves like the linear model. Remember KN, KS, and Frick, no stickiness. There's also some newer contact models called soft bonded and subspring network that we can do. So here's the idea. I'm going to show grains yellow here. This is just discs glued together. Every time there's a parallel bond, I'll do a visualization. I'll just draw two black lines from center to center. So this is the bonded network, parallel bonded network. This is the collection of clumps. I have three shapes. I have disc shaped, disc shaped. I have two guys overlapped shape, and I have this weird three guys overlapped shape. And using all the same stuff we've done, instead of doing ball generate, I say clump generate. I can generate packings of these things. And this then would be the bonding network of a clumped material, a set of clumps if you throw them in there, right? And clearly what you're going to see is this is a very, very different microstructural system in how it's going to carry load than this system, right? That's why I'm talking about this vast microstructural space. And here I'm not even really changing grain size. Then on top of this, you could start putting size distributions of these two different systems here, right? Grains could also be, instead of balls or clumps, they could be rigid blocks. So this is, you start with a mesh generator that takes the cylinder and turns it into a tetrahedra. You then turn the tetrahedra into, in this case, this is a 3-deck model. You turn these into 3-deck blocks, which are just like PFC rigid blocks. You could do the same thing with PFC rigid blocks. And then you put some kind of a bonded contact model at the faces. And if you squeeze this thing and measure macroscopic response, it looks like this. If I'm a rock mechanics guy, I could say, oh, I just did a bunch of tests on rock, and oh, of course, this is what you see. Notice here we're doing triaxial tests. As we increase the confinement, we increase the residual strength. We increase the strength, the peak, and we also increase the stiffness. Look at that, slopes get bigger. This is all naturally happening as we increase confinement. So there's bonded tetrahedral grains, which is a freaking weird thing. I really can't think of the tetrahedra as grains. This is just a weird microstructure that's going to give you macroscopic behavior that's very much like a rock, but it's really not a measure of the microstructure. This is a more reasonable. You could think of this as these grains are like real grains for something like a granite. So these are Voronoi grains, and this was actually done with PFC 3D. These are rigid blocks. So we do a Voronoi tessellation on this region. We then put every Voronoi cell, turn it into a rigid block. In addition, we cut this thing. So we cut the rigid blocks so that now we have a cylinder. You can see where we cut these lines. Okay. And then we test this and we see the same sort of a thing. No confinement. It's a very brittle stress strain response. If you start increasing confinement, you increase the strength. You're also increasing the residual stress if you start doing large strain. Okay. This is more of the case of like a granular system, but you could bond this too. Holy smokes. Yeah, you could bond this. So here I've got balls. I'll call this, these are clumps. I'll call this a dyad. I'll call this a dolo. There you go. You throw them in a box, right? You could throw those in a box and pack them and you could bond them, right? That's almost for sure not a good model of a rock. Okay, again, the cement. It's the cement at the grain contacts that's going to define what I'm going to call now a PFC material. Okay, here's a whole new concept, a PFC material. And I'm going to call that material based on what its types of bonds are. So I'm going to talk about a contact bonded material or a parallel bonded material or a soft bonded material or a flat jointed material, or in this case, a spring networked material. These are all going to be different, fundamentally different microstructures. So I'm going to designate them as different types of material. Okay. So then, of course, a material is defined by its material properties. These are the microstructural properties of that type of material, right? These properties are not just the contact model properties. There's also going to be properties that control how the material gets put together to begin with. So if we're making a parallel bonded material, we first have to generate a cloud of grains of whatever shape you want from whatever size distribution you want, and you have to pack them together. You somehow have to get them packed together before you can bond them. So there's going to be a well-defined procedure, which we're going to call the material genesis procedure. And that procedure is going to have some parameters. The most important one of which will be, what is the initial confining pressure that you use before you bond them, right? The higher that initial confining pressure, the more overlap there is at the time we put in the cement, okay? What we're often going to do is we're going to set that initial confining pressure to be very, very small so that we kind of just have a mainly just tightly packed system without much overlap. That's what we're typically going to do. But that is a fundamental property of that material. So I build two parallel bonded materials, one of which I did a genesis pressure of 10 MPa, and the other one I did a genesis pressure of 100 MPa. And those are going to be very different materials, and they're each going to have different responses. Just like I have a sandstone formation where the sandstone got cemented at a certain confining pressure, and I have another sandstone formation with the exact same sand, but it was cemented deeper down with a higher pressure. Those two cores are going to behave differently, right? So you can see things are getting relatively complicated here. It's not just, oh, what's the KN and the KS and we're done. There's going to be sets of contact properties, but there's also going to be material genesis properties. Okay. I did a bad job explaining this, so we're going to spend 2-3 minutes. Look at this. Here we go. This is this. How do we get K equals AE over L? So there's our little thing. We assume it's a cylinder. What would be the equivalent stiffness in terms of those parameters, right? So we say for a uniaxial, we're just looking at the normal direction. So we can say stress, axial stress equals E star times strain. You with me, right? Stress equals E times strain. Stress in that system, if we applied a force F over area equals E star times strain. Strain is going to be delta over L. Now let's just rearrange this thing. And I could say F over delta equals what? Equals E star F over delta equals E star A over L, right? All I did is rearrange it, E star A over L. I got that right, right? And then F over delta by definition is K. With me? Force over displacement. That it's a force being applied to the spring. It results in a displacement delta. By definition, that's K. There we go. K equals E star A over L. That's where that comes from. So it's just the equivalent if we just had a little cylinder. So basically the idea is that that spring is going to be assumed to behave like a cylinder of elastic material in that little location. That's the idea. And so that's kind of remarkable because by doing that, then we can use E star and we can find that we'll get about the same E everywhere. Okay. Now let's resume the lecture here. Let's do a little roadmap. So we're going to examine each contact model. Okay. Let's examine it. The simplest, my most concise way of describing it without reading it. And of course, in the documentation, each contact model is described in proper full detail. This is the linear model, right? This is the basic core model that we use. This was the model that Kundl and Strack presented in their original paper that describes the distinct element method, right? So there we go. You know all about these plots now. There's really, it's just locally, it's two surfaces that are interacting. Top surface red, bottom surface green. There's a normal spring Kn. There's a shear spring Ks. Right? This stick is connected to that surface. This stick is connected to that surface. When you move in a shear motion, you load that spring. It's limited by a friction coefficient, right? Okay. Here's another thing. We actually have a parameter for this model called surface gap. What that basically does, it allows you to define an initial state of what the gap is to begin with. It doesn't have to be just touching, okay? And so you could, for example, have two particles that are actually not touching. So this is the distance between them. We call that the contact gap. That's the real distance between the particles. But you could say, oh, I want to pretend that the surface of this particle goes out to here. And I want to pretend that the surface of this particle goes out to here. This would be that gap that we would apply. This we apply this reference gap. This reference gap is going to allow us to make these surfaces not necessarily correspond. Okay, so it's a very powerful thing because it allows you to take a set of disks or other particles, and the fact that the actual surface of the particle does not have to be at the surface of the particle, if that makes sense. It's as though the surface was bigger or smaller. Okay. It's, for example, this would be used if you have initial overlap of particles. By setting the reference gap appropriately, those particles, even though they are overlapping, as far as the system is concerned, they're not overlapping and they're just perfectly touching. Okay, that's the idea of this reference gap this surface gap we can specify. Okay, enough said. Contact bonded behavior. Think of the linear model, but putting a really small spot of super glue on there. Okay. Notice now unbonded is the linear model, but bonded, there's no more friction coefficient because they're bonded. Now there's a strength, shear strength and a tensile strength, right? That's the contact bonded system. Notice also the contact bonded system, the cement itself has no stiffness. There's no additional stiffness when we turn on the bond, okay? There's also, for this contact bond, because it's infinitely small area, there's no resistance to moment. If I apply a rotation to the top and fix the bottom, there's no resistance because I can't build up compression and tension. That's why I'm saying here the contact moment is identically zero for this contact bond, okay? This would be like a sandstone with a very, very tiny amount of cementation at the grain contacts, okay? Parallel bond basically provides two interfaces. It provides the surface-surface interaction from before, but it also provides this cement. And so think of the cement as a cylinder that's glued. Think of it as a cylinder between the two that's been split down the center. Half of the cylinder is glued to the top, half of the cylinder is glued to the bottom. There's an interface there. That's what the parallel bond behaves like. Okay. So notice if it breaks, it's just the linear model, but if it's bonded, there's an additional stiffness in the normal and shear. So there's an additional stiffness and there's then a tensile strength. And instead of a shear strength, there's a micro cohesion and micro friction angle. Okay. Again, trying to show that idea, right? There's the parallel bond material, right? If it's broken, the parallel bond material is gone. There's just this interaction, right? Otherwise, there's this interaction plus the force and moment in the parallel bond, okay? A key element we're going to find out is this is an issue that makes it not behave in many ways like many rocks, is that this thing is either intact, it's bonded, and it's fully elastic, and it resists moment, it resists all the different moment, the twisting moment, the bending moment, the shear, it resists all that elastically, but then if it breaks, it's gone. So suddenly all of this moment resistance is just gone. So it's sort of like, this guy, it broke. It's just not there anymore. It's not doing anything anymore. It broke clean all the way across, okay? Now there is a other type of model. If you have the parallel bond model, we take the parallel bond model and instead of just having it break instantly, you can have it do what's called softening. And so what that means is, think of it like this, it's bonded and now there's this softening. I showed this here in the normal direction it can soften, meaning this is like viscous caramel. And so if you had caramel there, if you start pulling on it, it doesn't just snap, it starts to slowly neck down and the stress that it carries gets less and less and less as you continue to stretch it. That's what this soft bond is. It's a parallel bond with tensile softening. And so that's what this kind of looks like. This is like this outer fiber stress here. These are the two surfaces. The two surfaces are getting rotated relative to each other and they're getting pulled. We compute the outer fiber stress. That's what sigma is. This is the distance between them. And we basically notice that it goes up. The stress here is tensile. It gets bigger and bigger and bigger. If it was a standard parallel bond, it would break and the stress would drop to zero. In this case, as you continue to do this, the stress slowly goes down. That's called softening. If you unloaded it, it would do this, same stiffness, go back up, continue to soften. And you can control all kinds of things. You can make it break before it softened all the way to zero. Okay, that's called a soft bond. Sometimes, for reasons I'm going to talk about in a little bit, you might want to have a contact that has continuing moment resistance even as it starts to get damaged. A more realistic thing might be that you get partial damage along that interface and not just complete instant breakage. Okay. That's the reason we have this model. Okay. What is this model? There's a lot of pictures on there. Let's forget about those pictures. Let's look at this picture. This is a 2D image of what we call the flat joint contact model. What's it trying to do? It's trying to behave like polygonal grains that are interlocked. Okay. But it's going to do that using spherical particles or disks. So what it's going to do is at the here's a disk 1, disk 2, here's a contact. It's going to make that contact behave as though it had this length, and it's going to allow that contact to partially break along until it finally becomes fully frictional. So here's the idea. Here's the top. I'm showing this for disks. Here's the top, here's the bottom. Just like the parallel bond, think of this as a surface. That's an interface now. It's a surface glued to this. There's a green surface glued to this. They move with these guys. We can think of this as an interface now. This interface itself is going to be discretized into elements. Okay. Each element now individually can be bonded and can break. And after it breaks, it's frictional, independently of each other. So this is a contact model that internally you can think of it as having 4 subcontacts, each of which does a simple thing. In 3D, this is a disk and it gets discretized like this, and you can control the discretization. So what does that mean? This is what this system looks like. Look at the 2D thing. If I actually try to draw a way of visualizing a flat jointed system, it looks like this. Here's a grain. It has 1, 2, 3, 4, 5 contacts. I'm going to say they're flat jointed. One of the parameters of the flat joint is the radius. So you're specifying this radius here, R, okay? And so for this system now, this is what this would look like. It's as though this disk suddenly had this shape, and this part here had this shape, right? And so now this is going to be very interlocked, okay? Because it's discretized and each guy has its own springs, there is stiffness. So it's deformable. The interface itself is deformable. It's also breakable because each little element can break independent of the others, which means it can have partial damage. In 3D, it looks like this. I love this picture, right? So you can think of the grain. I'll call it a faced grain. It's still rigid, but it has these interesting facets on it, okay? This is extremely powerful because notice, this is an initial packing, let's say. Notice this guy's not touching, this guy's overlapping, those guys are just perfectly touching. This is my initial packing I got somehow. This ball now, if I create flat joint contacts at those existing contacts, one of the parameters that I specify for a flat joint contact is the initial gap. Okay, which means that these guys, the surfaces are just touching, but I don't care. I'm putting an interface in there and I want to make it as though there was an initial gap, G0. So this grain now looks like this, and this grain looks like this, and I put in an initial gap. This guy, the surfaces are not touching. I don't care. I'm going to put a 0 initial gap in there so that it looks like this. It mechanically behaves like this. So I've decoupled the initial configuration of the packing to the actual microstructure you create. This allows you to take a packing and to say, I'm going to make a flat jointed material, and one of my parameters is the gap. So I'm going to give a normally distributed set of gaps that correspond with the normally distributed set of initial microcracks in a rock. Boom, I got a whole new microstructure. That initial gap distribution is hugely important in controlling many of the properties of the system. Okay, this is what it looks like in 2D. This is what it looks like in 3D. You can see the same idea. That's what this microstructurally, mechanically, the system is going to behave like this. Okay. Then they can start to fail individually. So here's the idea in 3D, right? I fully fix the bottom. I take the top one and I apply a a rotation to it, which means this side lifts up, this side compresses. And now I'm going to say when a bond breaks, I'm going to call it a crack. So when an element breaks, in this case, there's 16 elements. They're all independent of each other. This guy broke. So I'm going to draw a little hexagon here. That's going to say that's the micro crack. So in this case, when I rotate it like this, all the guys on this side went into tension and broke. These guys are in high compression. They're not going to break. So notice I have partial damage. This case, between these two faced grains, I've loaded this already. This is like during a compression test. This originally had 4 elements, so all 4 are broken. You can see they're all 4 broken. This guy, it's hard to see, but this guy has 3 of them broken. This one is in compression. And thickness in these plots is related to opening. We're going to see some very amazing plots a little bit later for the perforation damage work, where we can actually see the evolution of this damage and this partial damage as we load these things. Okay. And this is just demonstrating this interlock that you get. So look at the 2D system. This is my initial system now with the flat joints. That's really what it mechanically looks like, even though it's just spheres or discs. Fix the outside ones, don't let them move. Force this to rotate. Notice compressive force builds up, a little bit of a less compressive force. There's no bonding, so there's no tension can develop on that side. But of course, it's interlocked. So even with no bonding, it's interlocked. If this was a parallel bonded system and the bond was not there anymore, there would be essentially no rotational resistance. There'd be no interlock. It turns out that for many rocks, for most rocks, you need to have interlock between the grains. And if you start doing a UCS test and everything just fully fails like that, you don't get as much interlock. That's going to be manifested by the fact that you're going to be able to match a tensile strength, but you're not going to match a high enough UCS. And we'll show that a little bit later. Okay, so that's this flat jointed contact model. Just a couple of slides. This is new stuff. This is the stuff of my recent research, and I just found this out last fall. So we created this thing called a Subspring network Voronoi model. Okay, this is the idea. The idea is that here is a cross section of a granite, and you can see it's very complex shaped grains. They're not actually polygons. Marble is much more polygonal in its grain shape than granite. But I'm going to say we can approximate this as Voronoi cells. So these are Voronoi cells. They perfectly fill space because they were created as a Voronoi tessellation. And then we put rigid blocks at all those spots. You can see how they're shaped. Each one of these in 3D has approximately 12 to 14 faces. And then what we do is we put in a special contact model called the Subspring network contact model. And so what's that? That's basically behaves, don't look at all these details. It basically behaves like the flat joint system. And so this face here has this Subspring network contact model. This face behaves as though it was a circular cross section that had the same area as the face as the face area. And what it then essentially does is it says, here's my subcontact, here's a subcontact, here's one, and each one independently can carry tension, can carry shear, can break. After it breaks, it's frictional. So this system is going to exhibit interlock even after it starts to break, and it's going to exhibit partial damage as it starts to break. Okay. One of the things we can do with this, and I don't have time to describe this in the proper detail, is because we form this network of springs, and this network corresponds exactly to this partitioning of space, and these partitions perfectly fit together okay? Which is not the case if you have a bunch of spheres packed together and you have contacts. They don't perfectly partition space. This does. Because it does, we can magically choose the value of Kn at every single face such that the macroscopic thing will exactly match the desired Young's modulus. So a parameter to this system is E. It's not just some E star that's proportional to E. It actually is E, and that's what you'll get if you squeeze it. Okay. There's also a way that you can specify nu, the Poisson ratio, and you can get that. And we're not going to talk about how. This then allows us to build up a model, and we're going to, and here's the model that I have built up. And this is the parameters. This is the Cadillac of all models because it has a huge number of things going on in it. This is the model I said that is matching all of the characteristic stresses. This is the first time I've ever seen any bonded particle model match all those stresses. The high level description, these are the parameters for the thing. So these are these elastic constants at every single contact. If you specify every single contact micro E to be the same, you will get the macro E that you want. But if you give a distribution of micro E's, you will get a distribution of heterogeneous forces, and you can control that. And so you can control that by controlling the distribution of these micro E's. That's what this E bar is. And this is showing if we're using a Weibull distribution. And so this is this thing called the Weibull modulus. And for those of you who don't know, what it does is control the spread. So as we make that Weibull modulus higher, this is the Young's modulus. This is the probability density, right? So this is basically, most of them are about 80, and they have a spread. They go from 60 to about 100, right? As we decrease M, we get a bigger spread. So this is giving you're assigning a heterogeneity to the microstructural moduli. You're also then giving strength at the interfaces. So we're giving a tensile strength, and we're giving a distribution of tensile strengths, because for a real rock, all of the micro tensile strengths are not going to be the same. So again, there's a distribution of strengths that we're given. And then we're giving basically a tensile strength, a cohesion to tensile strength ratio, a friction angle, and a residual friction angle for this system. Then we're actually able to put in initial gaps and slits at each of these interfaces. And so we can basically say some of them are going to they're perfectly touching and they're bonded. Some of them are perfectly touching with no bond. Some of them have an actual gap. So we can specify the volume fraction of each. This initial microcrack fabric is very important. This is giving us that initial stiffening in the UCS stress strain curve, so that we get, because we're closing these up, we're getting crack closure. And then I won't go at all into this, but we have a concept of breakage of the grains. And there's 3 modes in which these grains can break. Okay. Let's not talk about that. So that's enough said. That's the Cadillac of all models. That's the most recent, latest, sexy research that we're doing with this stuff.